And I want to move this guy's bad. Okay. Let's go ahead and look at this. We'll try to go pretty quick, but let's take a look at our graphs. All right, so we did this, like I said, yesterday. We did it very general, and I copied it on the wrong side as far as the 3 holes, so make sure that you're seeing where it says section 3.1. We'll do that one first. All right, so where is an absolute max? This is actually probably the hardest one. There is none. Why would there not be an absolute max? What is that? Beautiful. Yep, because you should go here, but what's there? An open circle. And so because it's an open circle, remember, it is okay for an absolute to be at the end. It just can't be local. So this is absolutely right, but the open circle causes it, because let's see, what is it? 1, 2, 3, 4, 5. Okay, but it's not at 5 because it's an open circle. So as soon as you say 4.9, then someone can say 4.99, right? 4.999. And technically, we never actually reach 5, but it always gets bigger and bigger. Now, the limit would be 5, right? Because the limit is what is it approaching. But for this, we want an actual value, and so it could just always get bigger. So this is, again, these are the technicalities. These are a little bit harder, but just understand the open circle causes it to not exist, okay? How about, do we have an absolute min? Another thing I was going to mention, if it says values, it actually wants the y value. I wish it was a little bit more clear, but if it says value, it's talking about the y value. Okay. All right, so absolute min down here, and the y value is 1. Okay, remember you're doing the y value. All right, local max. Local max, anything high in that area, and give the y value, which is kind of weird, but it wants the y value. So 1, 2, 3, 4. And do we have another one? So maybe I can mark it, this point here. And then do we see it would be over here? 1, 2, 3. Those 2 high points. Those are local maxes. All right, how about local mins? Well, I had an absolute min at 1. That is also, as long as it's not an endpoint, as long as it's not an endpoint, then it is also a minimum. Okay? As long as it's not an endpoint, then it also falls as a local. Let's see, is there any others? And again, this is kind of a technicality. We're going to go ahead with this guy. So we're going to say a y value of 2, not this one. Do we see that? Remember, endpoints can't be locals. So we're not doing it with this one, but we're doing it because of this. I wrote, for this guy, I wrote when x is 2, not when x is 7. Does that make sense? And again, this one's a little weird because there is a jump there. But what's the definition? Is it the lowest in the area? So if I cut here, that would be the lowest in the area. Again, most of our graphs are continuous, so don't freak out too much. These are kind of like all the exceptions, or try to toss them in together. How are we doing? Okay. All right, and then this one is just, can you sketch if they tell us it is continuous from 1 to 5. Now those are X values. What else? Absolute minimum. And this is weird too. If they say at, they're giving X values. All right. So if they just say the word values, they're talking Y. If they say at, then that's an X value. So that's a little crazy. And then an absolute max at 3, so that's an X value of 3, and a local min at 4. Now, no one's graph has to be the same. It just has to meet these requirements. So from 1 to 5 is where I want my graph. So from 1 to 5, they're brackets, so they're going to be closed dots at the ends. An absolute min at 1, an absolute min at 1. So that means my graph cannot go below there. I just randomly picked a point, but it cannot go. That's the absolute. Absolute max at 3. I can put it wherever. That's going to be my high point. And then a local min at 4. So it's got to be higher than my absolute. A local min at 4. I cannot go past this, so I do have to start here. I'm going to go up. That's going to be my absolute max. This is only local, but I have to turn around there, right? Oh, and then 5, I do need a closed point because it's closed. So, but this has to be a minimum. So I have to go back up. It's not maybe there. Why would it be wrong if I was too general with this point and I put it up here? What's wrong with this? I've changed my absolute max. Okay, you just kind of have to read it as you go. You can always erase, so do it in pen. But yeah, this would be too high. This would now be my absolute max. Something in between there causes this to be a local minimum, but that still is my maximum. I think on the homework, you just click around, okay? But you might want to try it just so that you get an idea, and then you can click around and see if you're right or wrong. It just kind of reinforces what these words mean. I like that problem, even though you just have to click. It is a pretty good problem. Okay, we don't want to spend too much time. All right, let's take a look at 3. These are actually from our book, but they didn't make it to website. So let's do them real quick because I do actually kind of like these problems. All right, so what's our absolute max? Do we have one? Absolute max, and then you just read the letter. So absolute max would be at, because remember we're doing technically X values. So we would say at, who wants to try? Absolute max at, what did you say? Say it again. It is at C. It's not at C, because I think there's something a little bit higher. It's pretty close, but what's even a little bit higher than C? S. Yeah. Now remember, can it be S? An endpoint can be a maximum. It just can't be a local. Endpoints can be maximum. So that's why I really like this problem. This one's perfect. All right, how about absolute min? Good, we're doing okay. Absolute min, and again, these are pretty close, but I think the lowest one is R. All right, let's even do this. Let's do local max and local min. S was an absolute max, R was an absolute min. How come I'm not going to use S for local, but I am going to use R for local? Does that make sense? because if S is an endpoint, it can be absolute, but it cannot be a local. Right? But R was not an endpoint, so it automatically falls in as a local. All right, do we have any other local maxes? A wouldn't be a bad answer except for what? It's an endpoint. Toss it. We don't even worry about that. Our next local would be C if we're doing maxes. And I think that's it, right? What about D? Is D a local max or min? Or nothing, right? Of course, right? Textbooks have to give you one where it doesn't fall. So we're not going to use D at all. Okay. All right, and then a local min is R. Do we have any other locals? B. All right, let's try it one more time. This one's just a little bit trickier because we've got some open circles and things. All right, do we have an absolute max? Absolute highest point is what? R? Perfect. And, you know, we can even do this. We can go to local max because it's not an endpoint. I can stick it there right away. If it's not an endpoint, then I put it there. All right, do we have an absolute min? I think we do. How does it show up? It's a little, nice to look too. I believe this is an open circle and this is an open circle. And everything else is closed. So our absolute min, our lowest point is A. At an endpoint, so I'm not going to put it for a local min. Okay, so any other high points? How come I am going to say B? Not because of this guy, but because of this guy. And that one's closed in. So that would be a local max. And I think, how about C? Is C considered a local max? No, because it is an open circle. C is an open circle, so it is not, remember the open circles cannot be, because you can always do 2.9, 2.99 or whatever it is. So this guy's colored in, so we're going to do a B. This one is not colored in, so that will not be a maximum. Right? And then we already got our R, so that's it. And then what else do we need? We need our local mins. Okay, where do we think a local min is? D. And that's our only local min. That's it. We can't do an endpoint. This is an open circle. This is a endpoint, so we can't do that one either. And B, how come B is not? Or
well, I was just going to ask, how is B a local max?
okay, so no, that's a good question. It looks like this. All right, see that? Okay. So we are considering, remember, there is no point here. So when I identify B, what is the only thing I'm identifying at B? The only thing at B is this guy. And that guy's a local max because in the area, that's the highest thing. Does that make some sense? And again, don't panic, but I'm glad you asked. I mean, now's the time to ask, but it's only a technicality. So it's not going to be a huge ordeal. But if you can even grasp that now, you're in great shape. This point is the highest in the area, and that's at B. Technically, there's no graph down here at B. We just put an open circle to kind of help people understand that it's coming really close to that, but it's not hitting that. Does that help a little? Yeah, that's a great question. Good.
Why can't we use like the point building on C for like a local min?
Because if, okay, that's a good question too. I like that. If I cut, like, let's say I cut here and here though, is this the lowest point? Can you see that? Yeah. Is that the lowest point in that area? You have to go a little bit to the left and a little bit to the right. So that would not be considered then a minimum. Does that make sense? Yeah, so always you can even kind of go left and right and draw some lines and then say, hey, is that my lowest point? Yes. Local just means in that area. So if I have something like within reason, all right. So if I have something like this, every peak is a local max. Every time it changes direction, it's considered a max or a local max. And then every time it changes directions at the bottom, it's considered a local min. Okay. All right. Good. Don't overthink it, but I totally get that they kind of force you almost, I think, to overthink it, right? Easels. Okay. All right, let's take a look at some more critical numbers. So that's our main focus. Okay, first of all, if you didn't watch yesterday's video, shame on you. But let's go over what is a critical number, okay? Because that's what we're going to be doing today. All right. So it's a list of possible maxes and mins. Okay, it's a list of possible maxes and mins. Most of the time, the list I would say is like 90% correct, but every once in a while there's an extra. There's never any missing. It's only an extra. And so when we go through an example, I'll remind you that. But and we'll talk about that again. But it's a list of possible maxes and mins. And how's the list created? When the derivative is 0 or if the derivative doesn't exist. Derivative doesn't. And for us, pretty much, when the derivative doesn't exist is when you have a fraction and the denominator is 0. This would be when the denominator is 0. And we did a couple easy ones yesterday. So let's make them a little bit harder. So the directions are, I can maybe squeeze it on here if you're still kind of writing. Find the critical numbers. Oh, let's see what's that. Or, yeah, find the critical. Find the critical number. Give me every place there might be a max or min. All right, so remember the main point of this is to get a good sketch of a graph, because they were doing this back when there wasn't graphing calculators, there wasn't any of that. So these first few sections are all to help us make a graph the best we can. Right? And I'm going to show you a reason why, though, even with the graphing calculator, it's nice to know this information. All right, so I think we can do it. Let's just slide it up here. F of x is equal to a fraction, x minus 6 over x squared. X squared minus 2x plus 12. All right, so actually maybe to find our critical numbers is when the derivative is 0 or the derivative doesn't exist. So the first thing you have to find is the derivative. Okay, when in doubt in chapters 2 and 3, find the derivative. Okay, so and what do we have to do for derivative here? We need to use the quotient rule. Okay, who's excited about that? All right, so f of x is x minus 6. What is its derivative? And remember, this is just, we're not talking about this f of x anymore. We're just talking about the general numerator denominator. At least we get lucky. What is its derivative? 1. Yeah, that's great. That goes to 1 and that goes away. All right, and g of x is x squared minus 2x plus 12. And its derivative is, roll it down, subtract 1. Roll it down, subtract, or yeah, the 1 goes then to a 0, right? But you still subtract 1, goes to 0. Okay. And then, oh, where are we at? Time to make my marks. Okay. All right. And then we're going to do, let's write it at least over here. Remember, it's G, derivative of F, minus F, derivative of G, all over G squared. So let's plug that in. So I'm going to mark this as now the official function derivative. G is that trinomial, x squared minus 2x plus 12. Okay. But at least I get a little lucky because what do I have to take that times? The derivative of f, which is actually just 1. Okay, if you want to write it for now, you can, but we don't really need that. And then minus f of x, which was the x minus 6. And the derivative of g is 2x minus 2. Okay. And then all over g squared. Okay, and then let's just simplify the top a little bit. Here, which means we have enough room. All right, so the top, we don't have to distribute the 1. That doesn't change anything. Just be careful here how much writing you want to do. Well, just be careful, minus and then bracket, because you have to FOIL and distribute that negative. You must FOIL and distribute the negative. So we'll FOIL first 2x squared, outer negative 2x, inner negative 12x, and last plus 12. And then all over. And if you don't want to write this yet, that's okay. Let's see, that's my paper. All right, let's slide this up. Is that okay there? All right, so now we got the derivative. Let's write it one more time. X squared minus 2x plus 12, because now you got to distribute negative 2x squared. Oh, we could combine these. This would be what? Negative 14x. And then if we distribute the negative, it would be plus 14x. And then minus 12. All right, and maybe instead of putting in the denominator, let's rewrite it one more time. Let's collect like terms. So this would give us negative x squared. This would give us 12x. And then these actually cancel, don't they? Okay. And then if we haven't done it, x squared minus 2x plus 12 squared. How are we doing? Next year I should put that on the test next year. Then we could just reference it again. Okay. Yeah, question.
Would it be like x cubed minus 2x squared plus 12x on the left? You were saying because you got to distribute the x in the beginning.
For
this guy?
Yeah, like scroll up on your paper.
Yeah. Okay.
Oh,
No. Wait, are you sure?
Yeah, you're right.
So this guy's derivative was only 1.
Yeah.
No, you're okay. Hey, no, that's you're fine. Does that work?
Yeah.
Okay. Yeah. Hey, always check, because if you make that mistake, I can do it just as easily. So yeah, make sure. So just bring those exponents down. Which thank goodness, right? Because then we were able to actually put more together. Okay. You're okay. Okay. Now, all that for the derivative. Now, what are we doing? Back it all up. Okay, so last chapter we were done, right? This chapter, we now use the derivative to find critical numbers. It's when the derivative is 0 or doesn't exist, okay? So we want to put a 0 in for the derivative. Now, how do we get, I think we did this, oops, see, and I made a mistake. The first week of class, I think we were doing it for rational functions and stuff, but how do we get a fraction equal to 0? The only thing we have to care about is the numerator. So we really just have to worry about this guy. Can you see any of that? Oh, maybe I'll zoom out a little bit. Get a few more lines on there. Okay. And so this I would probably factor. Zero product property. We could take out, it's up to you. I would probably take out a negative x, but if you don't take out the negative, that's okay. If you take out the negative, then this first, there's an x left over, and then it would be minus 12. And so that means that x is either, what would make this 0? Literally a 0, right? And what would make this 0 would be a 12. Now, are we okay? Should we back that up? Do we see how, remember, you set each thing. So technically you would set negative x equal to 0, and you would set x minus 12 equal to 0, and then solve each one. Okay. Now, couple things. What are these numbers? They're the critical numbers. They are the only place that there could be a max or min, a local max or min, right? So could there be a local max at 7? Absolutely not. Could there be a local min at 10? No. These are the only options. Now, is it possible that there's actually nothing happening at 12? Yes. Remember, this list, the only problem with this list is it's too big, never too small. Okay? But you still have to take into consideration where the derivative is 0 or where the derivative doesn't exist. And we really have to focus where the derivative doesn't exist when we have a denominator, and lo and behold, we have a denominator. But we get lucky. Okay? So how would we figure out, well, I guess we said it right here. When whatever makes the denominator 0 is where we would then have the derivative not existing. Where the derivative, when the bottom is 0, then the derivative wouldn't exist. Okay, now there's a whole bunch of things here. First of all, if we took the time to set this equal to 0, okay, if we set that equal to 0, there's actually no solution. So that's awesome. And our book actually always gives us that. But see if this makes sense. The original problem had the same thing, because that's squared. What's the first thing I'm going to do to solve this? I'm going to take the square root. And so I'm really looking at this. So that means that I want to see where the original problem doesn't exist. If it doesn't exist on the original problem, it's not even in the domain. So I don't even have to worry about it here at all. Let's do this. And that's why actually some calc books make you always first write the domain. So let's say, and this is not the case, I should have written a problem where it does, but let's say 7 makes the bottom 0. 7 makes the bottom 0 here, okay? That means that 7 is not in the domain. What would happen if I go here when I'm doing my derivative and I set the bottom equal to 0? What answer am I going to get here? I would get the answer of 7 again. But if 7's not in the domain, I can't put it in my list of critical numbers. Does that make sense? So you kind of have to be careful. All of these, the derivative is g squared. So if it's a problem with the original, it's going to be a problem with the derivative. But if it's a problem with the original, it's not even in the domain. Does that make sense? Okay, so the nice thing is we don't even have to worry about where the derivative doesn't exist for these, at least for these problems. All right, we'll do another one. We'll talk about it. But here's what I wanted to show you. This. I think if I zoom in far enough, it works better. Take a look. Okay, let's do this. Yesterday, we did this first one, x to the third plus 3x squared plus 9x. And this was the one where we got no critical numbers. If we got no critical numbers, what does that mean? There's no max or no min. So let's graph it. And sure enough, there's some curve. And now we could zoom out in different things, but chances are, if we didn't have any critical numbers, it shouldn't even be chances are. It makes sense that I don't see a peak or valley. Okay, let's go back to y. Let's try this one. This is what we did. I'm just going to do this one, x minus 6. That's the one we just covered. Let's graph it. That's pretty hard to see what's going on. But because I know I have critical numbers at 0 and 12, and those are x values, can we see that maybe there is a low point there? Do you see how without those numbers, I might not know that? Let's go to window and let's do y. Let's go from like -2 to 2. Now do we see how, yeah, there probably is a local min there. I just have to zoom in. Let's take a look at 12. At 12, it's even harder to see. So window, I'm going to go x, and I'm going to make it like, let's make it 20. When x is 12, does it look like there's a max there? Not really, right? So, but on my list, where was our list? Our list was 0 or 12. Could 12 be an extra and I cross that out? Possibly, but at least I don't have to look at 13. At least I don't have to look at 17. All I have to do is take a closer look when x is 12. So I can zoom in again. I'm going to go to window and I'm going to make, let's leave that, but let's do like maybe -0.5 and 5 or 0.5. Can you see any of this? That makes that really distinct. Okay, it's still maybe hard to tell. You can kind of see though, when it makes a little drop here, that it is actually going down. If you hit trace and hit 12, it's 4, 5, 0, 4, 5, 4, 5. You look at these numbers. And if you go in either direction, it gets a little bit smaller. Would we have picked out 12 as a maximum, even with a graphing calculator? Probably not. Okay, and so even having that, still knowing where those critical numbers makes a huge difference. Okay, now we still would have to, because 12 was in our list, we still would have to investigate, because remember that list could be too big. But with further investigation, it is a maximum. Cool. Huh? Okay, remember that's what math people get excited about. All right, let's try another one. We're only gonna have time for one more, and that's okay. Let's do, okay, now where am I at here? All right, let's do, and this was pretty, well, of course our book likes to make it hard. F of x equals x minus 1 over x squared plus 2. Okay, what are we doing? We are listing critical numbers, and critical numbers tells us wherever there could be a max or min. How do we find critical numbers? Set the derivative equal to 0. Set the derivative equal to 0. So we got a fraction, we got to do the quotient rule. F of x, and remember that's now just the numerator, is x minus 1. Its derivative, thank goodness, this guy, at least he does make it fairly easy. Its derivative is Geo. What is its derivative? 1. Okay, I put you on this one. You can do that to me too. All right, this is what? G of x is x squared plus 2. Its derivative is 2x. Okay, then we just plug it in. If you want to write it, derivative of g, or no, I'm sorry, g times the derivative of f minus f times the derivative of g all over g squared. right, plug it in. G x squared plus 2. Derivative is 1 again, so that's kind of nice. And then f is x minus 1, and derivative is only 2x. So that's actually really nice as well. And then all over x squared plus 2 squared. Okay, and that's, now we can mark this as the function's derivative. All right, so we don't have to FOIL. That's kind of nice. So the 1 just goes away. So we have x squared plus 2. Just be careful here. What you could do to save a little time is you could change this to plus and put the negative here, and then distribute the negative and the 2x together. Okay. Just make sure that negative gets to both, the 2x gets to both. Okay. All right, so it would be negative 2x squared, and it's actually going to be plus 2x. All right, derivative, here it is what? Collect like terms, negative x squared plus 2x plus 2, and then technically over x squared plus 2 squared. All right, that's our derivative. Last chapter, we were done, we were happy. This derivative, we got to set it equal to, not this derivative, this chapter, right? We got to set it equal to 0. But we get a little bit of a break, because how do we make a fraction equal to 0? We only care about the numerator. Now, remember I said our author's a hard guy. Plus 2x plus 2. This guy doesn't factor. If it doesn't factor, what do we have to do? Quadratic formula, okay? And that's another thing too, even with the graphing calculator, we would get the decimal approximation, which most of the time is perfect. But if we want the exact value, we'd have to do this, okay? It's up to you. Do we want to factor out a negative, or do we want to just leave it? Let's just leave it. Did most of you leave it? You can definitely factor out a negative if you want. Otherwise, that's all right. So x equals opposite of b, so negative 2, plus or minus the square root of b squared, minus 4 times a, which is the negative 1, and c, which is the 2. So remember, this is a negative 1, and that's a. This is b, and that's c. And then remember, all over 2, and a is negative 1. Okay, so now we just go to town. This is going to be what? 4. These two negatives are going to be plus, and that's going to be 8. So under the radical, we've got 4 plus 8. And then 4 plus 8 takes us to 12. So this is what x equals. Remember, this is what x equals. X equals negative 2 plus or minus the square root of 12 all over negative 2. Can I cancel the negative 2's? No, do not cancel the negative 2's. But can we simplify the square root of 12? 2 times 6 is okay, but why do we like 4 times 3 better? Because the square root of 4 is 2. Okay, so negative 2 plus or minus, I can do it off to the side here, 4 and 3 if we can see it. So the square root of 4 is 2, the 3 stays underneath, all over negative 2. Now can I cancel the 2's? Yep, as long as it's in every spot. So this goes to negative 1, this goes to 1, and this goes to 1, negative 1. All of these guys cancel. 1, 1, 1. This one I don't really need. It's okay if you write it. This one I don't really need. Now, here's the only problem. Besides, you probably can't see it. We don't really like the fraction if it's a 1. So technically this negative changes this sign, And this negative then would change this to negative and this to positive. So it is okay to write this as a +1. Technically, those signs are changing, but you got both of them anyway. Does that make sense? You could also write it like this if this helps you. You could write -1 over -1, and then plus and minus the square root of 3 over -1. That might be easier to see. You can split that up, and then you can see how this goes to +1, and both of these change anyways. Now, how do you type that into WebAssign? There is no plus or minus in WebAssign, which I kind of like because it reminds you how many answers do we have here? 2. You got to type into WebAssign 1 plus the square root of 3, and then comma 1 minus the square root of 3. Sometimes we forget. I mean, we just so often leave it as plus and minus. That's important because you've got 2 different places where you could have a max or min. Now, how come I don't have to check the bottom? The bottom is what makes the derivative equal to 0. Or, yeah, I'm sorry. The bottom is what makes the derivative doesn't exist, and I'm supposed to check that. But whatever makes the bottom of the derivative would have also made the bottom of the original problem. The bottom of the original problem, if there's an issue with the bottom of the original problem, it's not in the domain. Okay. So we don't have to worry about that. Tomorrow we'll have to worry about it. So today we only have 2 answers. All right, so today you're doing 1, 2, 3, 7, and 8. Did not get nearly as far as I thought, but that's okay. And then yesterday's was 4, 5, and 6. We might spend extra time on it. We have the day, I might use it, we'll see. But okay, so today you've got graphs and then just 2 more critical numbers. And these were critical numbers to begin with. These were a little bit easier and then they get harder. And then the 1, 2, and 3 are the graphs. Okay. All right. Try something tonight, don't get too behind, okay? At least try some of them tonight. I'm gonna stop this. How are you doing, Anthony?
Good. So I know I didn't